Hey, Dr. B here, and it's time for worksheet 7.12. This is the bonding review worksheet. This is a 3-pager, so I am going to go through this probably a little bit faster than usual since there's a very large number of questions. I can see already that some of the numbers are a little bit off, but hey, we can still refer to them. Okay, number 1. Use Lewis dot structures to show how two hydrogen atoms can form a H2 molecule. I would accept just a single bond between them, knowing that a bond is 2 electrons. So something like that would be fine. If you just draw a line, that was fine. This one is isoelectronic with helium, as is this. Let's do the same with a chlorine molecule. In this case, oh, look at that. We had some of them dots and some of them X's. You can see from whence they came. If you drew a circle like that, this chlorine shares 2 to get 8. This chlorine shares 2 to get 8. What a nice arrangement. H2O. Draw the lines. That's fine. Well, here it is with dots. 2 for each hydrogen, isoelectronic with a noble gas. 8 for oxygen, isoelectronic with helium. Great stability for each one. CH4 using Lewis structures. Single bonds on each one. Hydrogen's isoelectronic with helium, carbon isoelectronic with neon because it has all 8 valence electrons. CHCl3 is a little bit bigger, but it can be done, right? Put carbon in the center, it forms 4 bonds. Hydrogen forms 1, each chlorine forms 1, and don't forget the lone pairs. And if you drew a line, include the line on each one, they'd all have noble gas configurations. And if you drew the line around carbon with a big circle, it would too. O2 is going to require double bonds. But you could do the same thing. 2, 4, 6, 8, 2, 4, 6, 8, big circle there, and you're good. N2, well, that's going to require triple bonds. After all, nitrogen bonds forms 3 bonds, so that makes sense. They each have 3 bonds, and lo and behold, 2, 4, 6, 8, 2, 4, 6, 8 electrons. Life is good. Which one would be the strongest bond? No surprise. The shortest and the strongest bond would be the triple bond. Sulfur dioxide. We will draw this analogous to carbon dioxide. Is it sulfur dioxide? Now that one's hard to draw, right? We're going to have to draw that with, look at that, 2, 4, 6, 8, 10 electrons on the sulfur, and oxygen has its 2 bonds and 2 lone pairs. This requires a little bit of work, doesn't it? Hopefully these words will have some meaning to you. We add up the valence electrons. 6, 12, 18. We come up with 8 electrons for each oxygen. 2, 4, 6, 8. 2, 4, 6, 8. Don't forget about the lone pairs. And we're 2 short. We put the lone pair on the central atom, giving it a bent structure. Very interesting. Name the following molecules. AlCl3, aluminum chloride. As2O3, arsenic oxide. For arsenic, Nepasby. Is arsenic a metal or not? Actually, I think it is not. If it's not a metal, I don't have a periodic table in front of me, but it's right under nitrogen, right? It's right under phosphorus, so I believe it's a non-metal. Therefore, I stand corrected. I'm going to go with diarsenic trioxide. This one you wouldn't be able to name unless you recognize this ionic polyatomic ion right here as an acetate. So this is sodium acetate. PCl5, yeah, we better use monoditri, phosphorus pentachloride, and plain old boron. SaO2, we better draw the structure of it. We will treat silicon just like carbon since it's right underneath. 4 bonds, no lone pairs. And we'll connect it to oxygen. So we better use 2 double bonds and 2 lone pairs on each. There they are. On each oxygen. Looks good. Don't forget that this is a covalent network solid, so this can be a misleading structure. That would be your first approximation in theory, right? But if you looked at the actual structure, every silicon would have 4 bonds and there'd be a network of oxygens around it. Show the charges on each atom in the overall structure of ozone. Now, it does not have a ring structure which would fit perfect, so we're going to have to draw it like this. Do your best to draw it with 2 bonds and 2 lone pairs and realize that when you try it, it's impossible. Therefore, do your best to come up with something that's a little bit different. This is garden variety oxygen, but this one is 1, 2, 3, 4, 5 only around it, right? So it has short 1 electron, that's 6. This one has 1, 2, 3, 4, 5, 6, 7. This is negative. Some people refer to this as an internal salt or a zwitterion. The shape and bond angle of methane, well, when you place 4 things around carbon and spread them out as far as you can do better than square planar. You can spread out those bond angles to 109.5 degrees. That is a tetrahedron. Shape and bond angle of water, H2O, that would be the lone pairs occupy space, right? So you've got 4 substituents, 2 of which take up space. This brings the bond angle to 104.5 degrees with about a 96 picometer bond length. We call this a bent shape. Which molecule contains the strongest bond? I think the one with the triple bond, that would be N2. These ones are single, as are those. Say if it's ionic or what type of bond it is. ClCl, that is identical nonmetals, so nonpolar covalent. OF2, interesting. God, I've actually worked with that stuff. It's scary. Well, I guess if we put a fluorine around each oxygen, we have our oxygen with the 2 bonds and fluorine with the 1, and that's a covalent bond, but since it's oxygen to fluorine, it's more electronegative towards fluorine, therefore polar covalent. The sodium-oxygen bond is a metal to a nonmetal, ionic. The silicon to fluorine bond is metalloid, but not on the nonmetal side, to another nonmetal, but not the same, so we're going to go with polar covalent. If we can get it to show up. There it is. Okay, we do have 2 more pages, so take a break if you need to, but here we go. Next page. Name me. I would name this zirconium chloride, zirconium-3 chloride, because zirconium is in the polyvalent region. What are some differences between naming ionic compounds and covalent molecules? Well, they are substantial. Ionic, don't use monoditri. Covalent, do use monoditri. Ionic, if it's in the polyvalent region, use those Roman numerals. Covalent, just use monoditri. You should be good to go. Ionic, always go positive than negative. Covalent, we typically start with the one that forms the largest number of bonds, I think. Yeah, that's probably true. A hydride anion has the formula H-. Write the formula for calcium hydride. Well, it's -1, calcium is +2, so we will need CaH2. Ammonium carbonate is NH4 with 3 carbonates. There is no way, because each carbonate is -2. That's -6 accumulated on the right side and only +1 on the other. I think they got it reversed. It should be 3 ammoniums and 2 ammoniums and 1 carbonate. 2 + 1s offsets the -2. Well, that can't be right because hydroxides are -1. Each sodium is +1, so we only need 1. CH5 makes no sense because carbon only forms 4 bonds. I assume they meant CH4. And this is not ammonium hydroxide because NH3 is ammonia, not ammonium. We're short a hydrogen right there. This should be NH4OH. I don't know if it shows up. There it is. The oxidation states of each atom in sodium chloride. Well, when it's a formal charge, the oxidation state is the same as its charge, +1 and -1. But for CH4, we can assume each H, it's like carbon tetrahydride. Each H is -1, therefore carbon would be +4. We'll omit this for now, I think. What are the oxidation states for each atom in the carbonate dianion? Not an easy thing to draw. You would have, I'll just say the word C double bond O and then O- and O-. Therefore, oxidation states. The oxygens are -2. The carbon is +4, I believe, but we're omitting this also. You know, we're omitting the oxidation state questions, which I'm fine with. Difference in physical properties of metals and ionic compounds. Metals tend to be malleable. Metals tend to be ductile, meaning you can stretch them, and except for the groups 1 and 2, they're usually pretty insoluble in water. Groups 1 and 2 are reactive in water. The ionic compounds can form these nice lattices, which can be very strong, but due to the possibility of what we call frame shifting, just shifting that line of positive and negative charges and just shifting it by one grid, everything gets repulsive, and that's not great. Also, ionic compounds can have strong bonds, but not as strong as the intermolecular forces that can accumulate due to like extensive hydrogen bonding. So salts dissolve in water, most of them to a significant extent. Draw the structure of carbon dioxide, including lone pairs. We've done this before. Carbon will have its 4 bonds in the center, so put 2 double bonds and the 2 lone pairs on each oxygen. Ammonia, nitrogen forms 3 bonds, so draw nitrogen with its 1 lone bond and 1 lone pair and 3 bonds. Add your 3 hydrogens. Phosgene will require carbon doubly bonded to oxygen with those 2 chlorines attached to it. That'll give carbon its 4 bonds. Don't forget to put 2 lone pairs on each oxygen and 3 on each chlorine. And there it is. Last page. Which elements may be polyvalent? Well, the D and the F block for sure, and several of the lower P block are the most common ones. Looking at a chart can help to make it exact. Do polyatomics show up in the data booklet? That doesn't apply. This is for something called IB chemistry, and they don't. What's meant by coordination number? We can omit that for now. Does NaCl exist as separate individual molecules? Well, I think it would if it's a gas, which, by the way, would require so many thousands of degrees. But normally, no, it's part of an infinite sort of lattice. Compare the melting and the boiling point in terms of intermolecular forces. As they get stronger, both of those will increase. And I think we're talking about what happens when you melt. Okay, so when something melts, the intermolecular forces become fluid, if that's what's happening, if it's a covalent substance, right? Those intermolecular forces become fluid. If it's something like a lattice, well, the lattice turns from a fixed lattice into a fluid lattice. And once you break them completely, you have a gas. How do substances dissolve? I think if you're really thinking about it on a molecular level, you start with something that is bonded, but those the solvent comes in and starts providing its own intermolecular forces. If those are stronger than those bonds, the thing will dissolve. Solute, completely dissolving the solvent. Solvation is a term that may have not shown up in the packet, but that's what it literally means, is when the solvent molecules totally surround the solute. It means dissolved. What's hydration? Waters of hydration, for example. If you have a hydrate, like say copper sulfate dihydrate, that means you have water molecules that are bound to it. Those water molecules do not impart a charge. However, they are strong enough to be considered part of that substance. So cobalt dichloride, dihydrate, or any of those types of hydrated molecules are considered to be a single substance. An electrolyte is a solution that conducts electricity, and that means that a salt has been dissolved in it, like salt water. And a model that illustrates brittleness is that frame shifting model, when you have all attractive forces here, but if we take this bottom part of this lattice and shift it over by 1, can you see minus to minus, plus to plus, minus to minus, plus to plus? Crack. It's all repulsive right there. Okay, that is a review of covalent bonding.